Welcome to our final lecture of Basic Physics 1. We've been discussing sound and waves, and I promised you this time the last two topics, one having to do with the loudness of sound, and the other having to do with what happens when a sound source is in motion. So the loudness of sound is something that we can refer to as sound intensity. It has to do with the power output of the sound source, but also how far away you are. In particular, it is divided out, the sound gets divided out by the surface area so that it is a 1 over r squared relationship, just the same way that gravity is and that light is, and as you will learn in physics 2, the electric force and so on. So if we take what the power output is of some sound source and divide by 4 pi r squared, where r is the location of where the sound is being detected, that will give us the intensity of the sound. The units then are going to be in watts per meter squared. And so the intensity of sound is often discussed in terms of a decibel level. And so the decibel level gives us a logarithmic relationship to think about how loud the sound is. And it's given in reference to the threshold of human hearing, which is 1 times 10 to the minus 12 watts per meter squared. So this is your reference here of human hearing, but of course you could use this equation to compare decibel levels of other sound sources as well. And so this is what we would plug in for our I naught. And so different sounds are associated with different decibel levels. Something soft like a whisper is going to be 30 decibels. A busy street corner will be something like 70 decibels. A rock concert will be something like 130 decibels. And this is where you need to start thinking about, or maybe even before that at 120 decibels, thinking about ear protection from that level of loudness potentially damaging your hearing. By the way, the decibel level of one of those hand dryers in public restrooms is around this same volume of 130 decibels. So it's something that we should technically not be listening to with unprotected ears. So let's use this equation in a few examples. So let's say that you wanted to know, given that I've just told you that the decibel level of a busy street corner is 70 or 75 decibels, you want to know what that amounts to in terms of intensity level. What is it in a watt per meter squared? So we can take this equation that I've given you and plug in the threshold for human hearing and make sure we remember our rules for figuring out logarithms, right? So we make this 10 to the whatever in order to undo this side of the equation, which we have to do on both sides. So that gives me 10 to the 7.5 on the right hand side. And then when we do that, we find a intensity level of 3.16 times 10 to the minus 5 watts per meter squared. We can also examine this equation as it relates to, say, a loudspeaker system. And let's say, for example, that the loudspeaker system is advertised as having a uniform sound level plus or minus 3 decibels. What does that amount to in terms of a ratio of intensities? What does that 3 decibel difference mean? So when we subtract these 3 decibels and then we perform this undoing of the log, we will see that this amounts to the 3 decibel difference being 2 times is the intensity of the other sound. We could also ask ourselves what will happen when we have more than one sound source producing some sound wave and adding to the intensity. What will that give us in terms of a different decibel level? Say a trumpet player is playing a nice loud sound that is 75 decibels, but other trumpet players are going to join in now. If you have 3 equally loud trumpet players joining in, that gives you 4 trumpet players now instead of just 1. If I take a look at what the new decibel level will be, I will find that when I add it to the original decibel level of 75, I now have a new decibel level of 81 decibels. And the final example related to the loudness, we're going to think about what happens. I said you needed ear protection, for example, from something like a jet engine. What if you are 30 meters from that jet engine compared to 300 meters? What is the difference in the intensity levels at those different points and the decibel levels at those different points? So the sound level at your source is, well, not at your source, but at the closer distance of 30 meters is going to be 140 decibels. Now remember that sound waves dissipate like 1 over r squared. So if my r is now increased to 300 meters, we actually still have a decibel level of 120. So this is still a very loud sound even at 300 meters away, and this is why we need to take precautions and wear protective hearing implements. Okay, so the final topic related to sound is what happens if a sound source is moving. And that is that we will hear what is called the Doppler effect. So the Doppler effect occurs anytime motion results in some sort of change of frequency. For example, I'm sure you've all heard this before. You may be standing at a street corner and an ambulance is approaching you, blaring its sirens. When that happens, it is emitting wave after wave, but also getting closer and closer to successive waves and effectively squishing their wave fronts together, producing a higher pitched sound as it's approaching you. After it passes you and it's moving away, then it's still producing sound, but it's getting further and further away from each sound front as it's moving away. So this is like allowing the waves to spread out more and produce a lower frequency of sound. And so you hear that distinctive higher pitch as it's approaching you and lower pitch as it goes away from you. And so we can quantify that through the following equation. The thing that we have to bear in mind in using this equation is what the subscripts mean. By the way, this equation works equally well for light. Light also can exhibit a Doppler effect. It's just that we will plug in the speed of light in here, c, if we were using light, instead of the speed of sound. Okay, but for this equation, what we're doing is we're plugging in sound. We're talking about sound, so we're plugging in the speed of sound here. And of course, that will depend a bit upon your temperature, as we were discussing in the previous lecture. But given whatever it is, it will be the same in the numerator and the denominator. And then you have to account for any motion of the source, the sound source, and any motion of the observer. So for example, you could have just been standing here at the street corner, or you could have been driving in your car and approaching the ambulance, or driving in your car and driving away from the ambulance. And so we have to account for those motions as well if we're going to find an accurate frequency that you observe. So F sub S stands for the frequency given off by the sound source. F sub O stands for the frequency that you observe. And so whenever something is moving towards you, you know that its wave fronts are getting squished and it should be higher in frequency. So if you're wondering what sign to use here in the bottom, then you think about, well, what can I'm going to multiply some fraction by the frequency of the source, and I know when it comes closer to me it should be higher in frequency. So what sign do I need to choose if it's heading towards me, the observer? Well, I need to decrease the denominator if it's heading towards me. So this means motion towards. Okay? What if at the same time that it is moving towards me, I'm also moving towards it? Then I'm effectively squishing those sound waves even more and making them even higher in frequency. So if there's some added effect of my motion, it should serve to further increase that frequency. That will happen if I increase the numerator, and so I would need a positive sign here to add my observer velocity to the velocity of the sound source. So choosing these outer signs gives me motion towards. And so the ones inside, this one and this one, give me motion away, and let's check and make sure that makes sense. So once it's moving away from me, I know it should sound lower in frequency, so I want to decrease this frequency. That will happen by increasing this denominator to multiply it by something smaller here. So I will then choose this inside sign, so this amounts to motion away. It's moving away from me now. Okay, what if at the same time that it's moving away from me, I'm now moving away from it? The sound waves can spread apart even further. So I want to decrease this numerator to make this frequency even lower. And so again, that corresponds to the inside sign here, the minus sign. And of course, you could mix and match. It could be that the ambulance is moving towards me, but I'm moving away from it. Okay? Or maybe it's moving away from me, but I'm moving towards it. Okay, so that's how you would choose your signs here. But this one equation captures all of those possibilities in a generic sense, and therefore you can use it to compute what the actual frequency observed will be. If you look at the PDF that is associated with this lecture, there will be a couple examples of applying this equation. So I would like to ask you to go through those and make sure that all the steps in those examples make sense. And with that, we've concluded all the topics that I wish to talk to you about in Physics 1, and I wish you all the best in the future.